afternoon, ladies and gentlemen, our esteemed colleagues and distinguished audience of the second session of the ICPC 2023. A very warm welcome to this session of our conference. Today, it is with great pleasure that I have the honor to introduce our esteemed keynote speaker, Professor Monica Ferraris. Professor Monica is a renowned scientist in the field of material science and technology. She holds the prestigious position of full professor at Politecnico di Torino in Italy. Throughout her distinguished career, Professor Monica has authored over 200 peer-reviewed journal publications and holds an impressive count of 14 patents. With a remarkable track record in project leadership, she has overseen over 27 national and European projects related to ceramics, glasses, and composites with significant involvement in EU initiatives. While having leadership positions, including Vice Chair of the General Assembly in World Ceramic Forum, Coordinator Materials Group in KMM-VIN, Co-Editor-in-Chief of the International Journal of Applied Ceramic Technology, Professor Monica has made significant contribution to the field of material science and technology. Currently, Professor Monica's primary focus lies in the vital domain of joining and mechanical testing of ceramics and ceramic matrix composites. Without further ado, I invite Professor Monica Ferraris to share her insights and expertise with us today. The forum is yours, Professor. Thank you for joining us.
Thank you so much, Kashif. I couldn't be happier to be here, and I apologize to just joining your exciting conference for my presentation and nothing more, because as Kashif knows, I'm already attending another meeting. Look, this is my badge. It's a European conference, so I'm outside from this meeting for just for my talk, and then I have to go back. Sorry for that. So, and thank you also for this exaggerated introduction. I'm humbled. So just let me share the screen. Okay, this one, and you should be able to see it in presentation mode in 1 second. Is it okay? Can you see the screen? Can you see my presentation?
Can see the slides.
Can you see that?
Yes.
Okay, good. So the title of my talk is about etching of carbon fiber reinforced plastics, and the aim is to increase their joint strength. As Kashif already introduced, one of my main activity, probably the main one, is on joining of materials, and I'm very happy to talk to you about this new activity we have. Actually, it started with Kashif's PhD, so I'm more than happy to report about our progress on this topic. So first of all, a very few words about us. I'm actually in Spain right now, but usually I live in Torino, so Italy, and this is where the circle is. And in Torino, at Politecnico di Torino, we are a technical university in the northwest part of the country, close to the border with France. And we have quite a number of students on different branches of engineering and architectural studies. We are more or less 950, 1,000 faculty members. And my department is the Applied Science and Technology Department. I don't want to waste too much time. There are 2 links in case you want to have more information about our Polytechnic and our department, and about what we are doing. Well, in our research group, we are working on materials, in particular glasses, glass ceramics and composites, but also polymers for several applications, ranging from biomaterials to photonics to energy saving and storage, and of course, materials for the circular economy in order to recover waste. And then there is a subgroup of people working just on polymers. And well, in our group, which is called GLANCE, and you can see this is the logo of our group, We prepare and characterize custom glasses, glass ceramics, composites in different forms, bulk, as joining materials, coating, porous, thin films, and so on. We are quite a number in our group. At the moment, we are 5 full professors, 4 associate professors, and so on. All more or less, we are ranging between 35 and 40 people working on different areas. Well, we are quite a big number. And don't forget, a very important student of us, Professor Kashif Bangash, graduated from Polytechnic. Sorry, Kashif, I took these pictures from your Facebook yesterday. Good. So the aim of this activity is to improve the mechanical strength of CFRP joints. So just a very few words about CFRP, because you know that very well, much better than me. But anyway, we have carbon fibers, we infiltrate with polymers of different composition, we obtain CFRP. So why to join them? And why to study joining? Well, give a look to cars, for sure, cars. Well, here in Torino is, well, I put cars for the first. But also aircrafts. If you give a look, carbon fiber reinforced plastics is the pink part of an aircraft. Probably it is really even more right now. And then, well, aerospace, give a look to this structure of satellites. So how to join them? For sure, we cannot build monolithically. So we have to take CFRP, put them together to themselves or to other materials, metals, and then we have to join them. So since we cannot weld CFRP, adhesive or mechanical joints or both are the most interesting options. Well, adhesives, you can see there are some adhesive joints, maybe reinforced by an additional structure or a traditional metallic mechanical joint. But where is the problem? Weight, increase, and cost. So in order to avoid both of them and have a reliable joining strength, well, we patent a method to etch a thin layer of the matrix without affecting the fibers in order to have some sort of a composite joint. So I'll show you a very quick drawing about how we work. Well, somehow we hit the sample, the CFRP. This is our sample. And then there is an acidic etching, for instance, by sulfuric acid, this way. And the aim is to expose fibers without destroying them. Or if you do that on the other side, you can expose fibers on both sides, and then you can infiltrate your adhesive, and you end up with a composite joint. This is the aim. Well, we did it sort of, this is the lap shear strength of a two jointed CFRP together, non-etched, and then with different kind of etching. This process is really very sensitive to temperature and time of etching, of course, but if it works, you can double the lap shear strength, so you can go quite high in numbers. And why that? Because you have the CFRP and then you have the adhesive, but actually you have fibers, and the adhesive that you use infiltrate fibers, so you have sort of a composite joint. And if you give a look here, the structure, the shape of this curve is not is a brittle fracture. You have a sort of a composite failure also for the joint, so it works. It worked because when you change composite, well, the etching process is critical. So not always etched joints allow you to measure the shear strength, because sometimes the etching, if the etching is not perfectly controlled, the fractures can originate and propagate inside the composite, and you have delamination. So just to give you an example of bad results, very well disappointing results, the as received and jointed CFRP were all much stronger than the others. So the etching process has to be optimized, because otherwise, well, it doesn't mean that joint doesn't work. You can see there the jointed area here, the jointed region, but it is, well, the composite is affected, so you have a crack, and with a higher magnification, you see the joint is good, is sound, but then you have a delamination here because the etching is too strong. And you can see the look, the joint is perfect, but then you have the delamination. So actually you have the joining material separated for the two samples. So as an way of saying that the etching process must be optimized. By the way, all these results have been unpublished, and is the subject of another PhD study from Alessandro Benelli, colleague of mine at Politecnico di Torino, continued the Kashif's activity. So the joint strength, what we do is to do lap shear in compression with these two samples. So we use this standard size and shape in order to compare results, because this is not pure shear, it's just lap shear. And then, well, the goal is to do something better than the non-etched. And as you can see, if the etching is not perfect, well, you can have bad results and lower than expected. However, if the etching process is good enough, we start increasing the joining strength. So you have the orange one, which is not etched, and then gradually we start increasing with the etched samples. This is a I can show you. Oh, sorry, too fast. It's a long process, but if correctly done, can work. Now I move to another part of this activity, which is not just joining CFRP together, but joining them to aluminum alloys, because, well, if you want to build with this new material, sooner or later you have to join them to metals or to some more traditional materials. So you can see there the non-etched and etched behavior. Again, these are new composite and new joints that we are working on. The non-etched are a cohesive failure with no delamination, of course. And this etched one, well, the etching was really effective, too much, because you have on the aluminum side, you have part of the composite. So we are again in a situation where the etching is to be optimized. This is what we are doing right now these days in order to reduce the effect of this etching, but results are already quite promising. And last but not least, if you were joining, sooner or later, you had to work on mechanical testing of your joints. And we decided to use lap shear testing methods, even if it's not pure shear, because we can somehow keep everything constant and compare results of different etchings. You can see there our setup, which is you have aluminum here and CFRP here, and then we push on aluminum, or as I showed you before, 2 pieces of CFRP here. Again, this is not pure shear. We are perfectly aware that there are some stress concentration here and there, but it is at least one way, a simple way to test the behavior of many different etchings. We are now thinking about moving to tensile, but even with tensile, we have some issues with bending. So at the moment, we stay on lap shear, offset lap shear in compression. So another activity we are doing in parallel is surface modification of CFRP in order to improve the joint strength. Not just acidic etching, but we try to work with plasma treatment in air right now, plus in the future with different gases. And, well, as you know pretty well, is a way to clean the surface, not just to clean, but it's a way to activate the surface and to improve the joint strength. We have just started this activity on that. And then, well, I think this is more or less everything. Thank you very much for your attention. I apologize again because I have to leave, but I'm very open to every possible question and answer session you may want. And of course, we are open to collaboration. The name that you find here in every slide, JTech, with this single lap offset symbol here, is our new research center working now since 2021, dedicated to advanced joining technologies. Give a look to the website of this research center. Is inside the campus at Politecnico di Torino, and we are very happy to welcome you. And if you don't have time, just give a look to the virtual tour on the website. There is also a virtual tour, so you can see what we have. And well, thank you so much for your attention and for inviting me to give you this talk.
Thank you very much, Professor Monica, and we're grateful for sparing your time out of your busy schedule, even out of your own office. We are very grateful. We haven't yet received any questions, so maybe if there was any, we will email you. Thank you very much again. Hope to see you soon around.
Hope to see you soon. Bye. Thank you so much. Sorry again. Bye-bye.
Esteemed guests, I would like to introduce our next speaker, Dr. Ali Afzal from National Textile University, Faisalabad. His topic of presentation is development of textile-based medical patch as topical drug delivery system. I invite Dr. Ali Afzal to share his expertise with us today. Dr. Ali Afzal.
Good afternoon. This is our Good afternoon. This is a medical textile-based project, and in this project, we have developed a textile-based medical patch as topical drug delivery systems. In this project, we have developed medical fibers using different materials. As a medical fibers can be developed from biomaterials which can be of synthetic or natural origins. The key properties of such materials include the non-toxic, non-allergic, and non-carcinogenic. So these materials can be used in fibrous grade, or can be used in a membrane form, or can also be used in hydrogels, etc. So regarding the medical fibers, their specialized applications include the implantable materials, non-implantable materials, extra corporeal devices, healthcare and hygiene products. In addition, they are also used in topical drug delivery systems. which is a medication device used to administer drug to the body through the skin. In this process, we use different sort of formations, which include the cream, gel, ointment, paste, lotion, powder, etc., which we are actually using in our daily life. Uh, Apart from that, there are some other sort of form like fabric form, which can be a non-woven structure or can be a proper fabric structure which have drug incorporated on such carriers, and the drug can be penetrated through the skin from these reservoirs. Including the cosmetics, surgical sutures, lenses. Regarding the literature view, we are going to use polyvinyl alcohol and polycaprolactone, and both are these materials are biodegradable and biocompatible, and their applications are widely in different areas, including the cosmetics, surgical sutures, lenses. Regarding the literature view, we are going to use polyvinyl alcohol and polycaprolactone, and both are these materials are biodegradable and biocompatible, and their applications are widely in different areas, including the cosmetics, surgical sutures, lenses, tissue engineering, etc. So there is a lot of research being done in these particular type of material, but here this particular study is based on the co-extrusion of polyvinyl alcohol and polycaprolactone, which is not available in the literature. In acetic acid and developed a clear solution, and after the development of a clear solution through the agitation and heating, we add that solution in the dop tank of the extrusion machine. The extrusion machine which is used in this particular project is wet extrusion process, and that solution was kept overnight for degassing purposes. Later on, it is extruded through the spin rate of the wet extrusion machine in a coagulation bath. That coagulation bath was formed of ethanol. The material becomes solidified in a fibrous form, and later on it is stored after rinsing processes. So in the first phase of this process, we have developed the fibers, we have analyzed its properties, and we have observed the best possible concentrations or the blend ratios at which the best possible properties are achieved. So using that particular optimized material, we have incorporated a drug in the optimized blend ratio. And regarding the drug, we have included the sodium sulfur diazine as a model drug in this process in the top solution. And again, we calculated that particular drug loaded material in the coagulation bath, and again tested it for the drug delivery applications. Magnetic stirrer mixing for homogeneous solution preparation. Later on, the material is extruded in the spin rack, and later on it is coagulated in the coagulation bath made of ethanol. The fibers obtained were collected after rinsing processes. The picture on the right side explains the complete process. Concentrations do different type of materials in this project, which is the polyvinyl alcohol and polycaprolactone. In the polyvinyl alcohol concentrations, we have used 5 to 20 weight per volume percentages. Regarding the polycaprolactone, we have used 6 to 12 weight per volume percentages, and all of these different ratios are developed so that we can analyze the effect on different concentration of each material. So later on, we will achieve the best possible blend ratio, which will provide the required properties for the medical applications. Is the sodium sulfur-diazine as a model rock in the optimized blend ratio. The sodium sulfur-diazine used is in the range of 1 to 2 weight percent volumes, weight percent in the materials. Characterization, which includes the rheology, linear density, FTIR, and SEM analysis. Regarding the material characterization, we have used the tensile properties and elongation properties. We also have tested the comfort and surfaceability characterization through liquid absorption, swelling behavior, and the degradation test. And finally, the biomedical characterization is done for with respect to antimicrobial efficacy and drug release profile test. Regarding the rheology, it is observed that with the increase in the polyvinyl alcohol levels, the viscosity of the material increases. It is also observed that with the increase in the shear rate, the overall viscosity decreases. Polyvinyl alcohol concentrations, the material linear density increases, which actually explains that the material becomes more viscous, and hence because of the higher viscosity, thicker fiber material is achieved. As because the thicker material is achieved, likewise the tenacity of such materials also lies a little below, because the stretchings of the polymeric chains and the solidifications of the polymeric chains are not so much linear. In such regard, the tenacity of the material is impacted, and we can state that with the increase in the polyvinyl alcohol levels, the tenacity reduces. With the elongation, because the polymeric chains do not find a good time to align themselves, and hence such materials do not show good tenacity and elongation behaviors. Observed in different solutions, with uh, in 3 different solutions, which is the distilled water, saline solution, and the solution A. The results show that with the increase in the polyvinyl alcohol levels, the swelling percentages increases in all different solutions. Regarding the PCl, it is also observed that the swelling reduces with the increase in the polycaprolactone levels. Absorption gram by gram, or absorption percentages in 3 different solutions, which is the distilled water, saline, and solution A. It is observed that with the increase in the polyvinyl alcohol levels, the liquid absorption weight increases, which is exactly the same like in uh, the swelling absorption, the swelling behavior of the material. Regarding the FTIR analysis, we have shown here different FTIR spectrographs of materials, which includes the PVA, PCl, and the blend effect of PVA, PCl, and the top one is the co-extruded material with the drug. In the last one, it is observed that the drug having the sulfatizing group at 1440 peak is showing, which actually explains that and confirms that the drug is loaded in the material, and hence it can be used for the SEM analysis shows that the surface topology. The SEM analysis shows that the surface topology of the developed fibers are quite rough and having the linear lines, which actually shows that the material is during the coagulation, the materials becomes dried and solidified in such a stage that it becomes shrink at that time. The antimicrobial efficacy of the optimized fibers, including the model drug, shows that with the increase in the drug levels, the overall zone of inhibition increases. When we are going to see the control sample, which is F13, have no zone of inhibition, while the zone of inhibition is increases with the increase in the model drug. The bacterial stains used for the antimicrobial efficacy includes the Staphylococcus aureus, and it explains that in different solutions, which is the distilled water, saline solution, and solution A, our drug is released in a consistent manner, which is steep at the first, and later on from about 12 hours to about 70 hours, it is providing the drug consistently for a long duration. Alcohol polycaprolactone bi-extruded fibers. The drug can be incorporated and released from the developed co-extruded fiber. Developed fiber with drug exhibit excellent tensile properties, swelling properties, adequate liquid absorption, degradation percentage, and good antimicrobial activity with controlled drug release. The project number 94713. And we are thankful to the Higher Education Commission for providing the fund for this particular project. And contact me.
Thank you very much, Dr. Ali Afzal. The speaker is currently not available. If there is any question, we can share with Dr. Ali Afzal and he will get back to you. Thank you very much. Now I would like to introduce our next speaker, Professor Mehmet Karahan. He is affiliated with Bursa Uludağ University in Turkey. The title of his presentation is Natural Fibers and Their Properties for Composites Reinforcement.
Hello, my name is Professor Dr. Mehmet Karahan. I'm the head of the Vocational School of Textile Sciences at Bursa Uludağ University. The topic of my presentation is natural fibers and their properties for composites reinforcement. I'm working on composite materials, technical textiles, and topics of smart and interactive textiles as well. So the objective of the study is a comparison of 5 distinct natural fibers, including jute, hemp, linen, sisal, and banana fibers as composite reinforcement. The characterization methods that have been applied in this study include scanning electron microscopy, tensile testing, Fourier transform infrared spectroscopy, thermogravimetric analysis, differential scanning calorimetry, energy dispersive X-ray spectroscopy, and Raman spectroscopy. Due to the SAM results of jute fibers, as you can see here, with 50 times, 200 times, 500 times longitudinal magnification, and also cross-sectional view with 300, 500, and 1,000 times magnification. Jute fibers are straight cylindrical. They have hollow structure, and also jute fibers have some notches on their surface. Regarding hemp fibers with the same longitudinal and cross-sectional magnifications, hemp fibers are rod-like, and they have some notches on their surface also. In case of linen fibers, they are also rod-like. They have some notches on their surface. The smooth surface of linen fiber provides it more softness than other natural fibers, and this makes it popular in clothing fabrics, particularly for women. Regarding sisal fibers, they are straight, cylindrical, and sisal fibers have hollow structure. Banana fibers are also straight, cylindrical, and they have hollow structures. Banana fibers are a more practical solution for better moisture management and air permeability due to the surface grooves, as you can see from scanning electron microscopy results. Banana fibers, owing to their roughness, cannot be used as a substitute for linen fibers in clothing fabrics. Tensile strength and elongation test results for different 5 natural fibers. As you know, the tensile strength and elongation is carried out in order to figure out the capacity of a material to withstand the tensile load before failing. So here we can see the result for jute, hemp, linen, sisal, and banana. And here we can see the force elongation percentage graph for 5 natural fibers. The graph contains 2 separate regions. The first region is an elastic zone, and the second is a plastic region. The area in which the curve deviates from its intended direction is addressed as the elastic region of the fiber. Sisal fiber has the highest breaking strength. Banana fiber has the greatest elongation. Sisal fiber has a lighter diameter or thickness than the other fibers, as demonstrated in the SEM examination. And as a result, it has a higher tensile strength. Hemp fiber has the smallest thickness and diameter among the fibers. It also has the worst tensile strength. Linen fiber has a slightly higher thickness than hemp fiber. It exhibits slightly better tensile strength. The chemical structure of natural fibers is brought in this table. They are all containing cellulose, hemicellulose, pectin, lignin, wax, as you can see here. Regarding the FTIR results, the OH stretching vibration is related to the broad peak at 3,000 to 3,600 centimeter over -1. The asymmetric and symmetric CH vibrations from the CH2 group of cellulose and hemicellulose respectively are represented by the peaks at about 2,900 and 2,850. The carbonyl COO bond of stretching vibration of carboxylic acid in lignin or ester group is in hemicellulose causes the peak at 1639 to appear. CH2 symmetric bending in lignin, cellulose, and hemicellulose, and CH symmetric deformation of cellulose and hemicellulose are related to the peaks near 1427 and 1369 respectively. Regarding the TGA results, the TGA test results contains and consists of 4 stages. The amount of mass that is retained as the temperature rises is shown in the graphs as the weight percentage. For jute, hemp, linen, sisal, and banana fibers, weight reduction in the first stage was 6.9%, 6%, 5.6%, 6.7%, and 6.4% respectively. All natural fibers exhibit this tendency as a result of presented moisture. The quantity of residual mass in the TGA curve abruptly drops between 148 and 416 degrees centigrade. Depending on the type of fiber, the second stage, which involves the majority of the weight loss, begins at 148 to 234 and ends at 395 to 416 degrees centigrade. The temperature range where the rate of weight loss reaches its maximum value is thought to be when hemicellulose and cellulose start to break down. The main weight loss in this case occurs between 148 and 416 degrees centigrade. Compared to other fibers, the linen fiber contains the most cellulose. The DSC test results actually measures the enthalpy change brought on by vibrations in the sample's chemical and physical properties with respect to temperature. The evaporation of water from the fiber structure results in a large endothermic peak that emerges between 30 and 135 degrees centigrade. There is a large endothermic peak because water molecules have such a wide range of binding energies to the cellulose backbone. EDX is a technique that reveals an element's composition by analyzing its different constituents. As you know, carbon and oxygen were found in all of the natural fibers. The results revealed that all 5 natural fibers include calcium, iron, carbon, and oxygen. Regarding the Raman analysis result, the major peak at 1096 is indicative of the CO stretching mode of cellulose, but the peak at 380 is only associated with crystalline cellulose and is not present in amorphous cellulose. In order to conclude, I have to say that the sustainability of natural fiber-based composite materials has led to an upsurge in the application in various manufacturing sectors. Advantages of natural fiber composites include lightweight, low energy production, and carbon dioxide sequestration. Replacement of fiberglass with natural fiber removes the concern about the potential of lung disease caused by the former and is a move forward sustainable development. Natural fiber reinforced composites have developed significantly over the past few years because of their ease of production, lower density, high specific strength, and renewable nature. However, interfacial adhesion with a synthetic matrix should be improved with suitable surface treatment. It is very important to create a good interface so that the applied stress can be transferred from the matrix to the fibers. We would like to express our gratitude and appreciation to Bursa Technology Coordination and R&D Center, abbreviated as Butacom, for their valuable support in performing the tests and analysis. This was the end of my presentation. Thank you so much. Hello, my name is Professor Dr. Mehmet.
Thank you, Dr. Mehmet. Ladies and gentlemen, and esteemed attendees of this session, it is with great anticipation and honor that I introduce our next speaker for today, Dr. Rana Faisal. Dr. Faisal is affiliated with Northumbria University in UK and has expertise in battery thermal management, lithium and sodium-ion batteries, electrode fabrication, and electrolyzer design. His presentation for today is titled Advancing Battery Thermal Management through Polymer-Based Composite Materials by Additive Manufacturing. I welcome Dr. Rana Faisal as he shares his findings and advancements in this crucial domain. Dr. Faisal, the stage is yours.
Dr. Faisal, you may start. Your mic is off, and we are not listening to the voice. Can you please switch on the mic? Dr. Rana Faisal, can you please switch on your mic?
Yeah, so sorry about that.
It's okay. Thank
Can you see my slides?
Yes, we can see your slide, and also we can hear you.
Thank you so much. It's an honor for me that I'm presenting my group research work here. So basically, I'm Rana Faisal Shehzad, and I'm working with Dr. Shahid Rasool, and I'm from Northumbria University, and mostly our Dr. Shahid Rasool group, like our group, work on the battery thermal management system, battery recycling, and different electrode fabrication like anode and cathode materials. So today I'm presenting our group, like we are working on the battery thermal management systems. So we are the topic is advanced battery thermal management through polymer-based composite material via 3D printing and additive manufacturers. So I've got like through quick review on the battery thermal management system. Like a battery have a very complex electrochemistry. So the battery which are using in the EV cars, so the desired temperature of EV battery is 25 to 60. And if there is like more than 60, if the temperature is high, so during charging and discharging, it's impact the battery performance. So you can say it can fade the capacity, fast charge. If we charge the fast, so easily the battery capacity will start decreasing, and then the external thermal events such as the explosions. So we have to keep the battery in the operating desired temperatures. Otherwise, if it's between 130 to 150, then cathode decomposition. If it's more than like 80 Celsius, then SCI, secondary electrolyte interface decompositions. So that's why we have to operate the battery in the nominal temperature between 25 to 60. So for that, like many cooling system is implemented already, like in the industrial, Tesla, Nissan, and different company are using. So let's say like I'll also quickly go through the active cooling system, passive cooling system, I have hybrid cooling system. Now, mostly like EV industry, they are using the hybrid one. So because it's a mix of passive and active cooling, it's a mixture of passive and active coolings. So the problem with these system is that the system is very expensive, not efficient energy. Let's say if it's active cooling, so we need required energy to run the fan and move the different liquids in the pipes. And if it's a passive cooling, so probably we need a heat sinks, then the thermal conductor, convection, and different type of PCM. If we use the PCM, the leakage is the problem in the passive cooling, and then the weight issues. If we use the liquid and passive system, mostly they have a heavy in the weight, so that's why we are not using, still the company are using. So that's why we have introduced innovative battery thermal solution for EV batteries. So our novel composite material for the battery thermal management is basically a polymer. You know, the polymer, the cheapest source. So for the casing of the battery, it's like already using the companies are already using the polymer, but we can easily tune that polymers and convert as a battery thermal management system of the EV cars. So basically, we have done that. We have like the pure and composite material. So we have took like thermoplastic and we have mixed with different carbon based and metal based materials. In the carbon based, recently have worked on the carbon fibers and the metal powders and metal foams. So thermoplastic, like normally we use PLA, PVA, PETG and ABS. This is already like easily available and it's very cheap source for the polymers. So composite the filaments extrusion, then we have mixed thermoplastic and different carbon-based and metal-based material. And then we have make a filament and then we have printed. So you can see that we have printed different battery casing with the ABS, with the PVA and PETG, and we have also mixed like 80 to 20% stainless steel powder in that filaments. So optimizing of design and battery thermal manufacturing. So like over work, the 3D printing, first we have designed the casing of the battery and then we like print that design. But before that, we have used 3D filament maker. First, we make the filament. I will in the next slide, I will show you that how we prepare the materials. But in our case, like first we develop the design of the battery pack, then we 3D print and then we test that material on different charging and discharging rates. So this is like our material design through filament extrusions. First, we shred the materials so we can easily use any recycle PLA, PVA, PETG, and any type of, and then we dry it, then we melt it, and we use like 3D extrusion, and then we spool it, and then we print it. So you can easily see the process of making the filaments for the battery thermal management systems. Then the next stage is the printing. We have optimized because ABS, PETG, PV, and PLA have like the fixed temperature that we can print on the fixed temperature. But we have optimized because we have a mix 80% stainless steel with 20% PLA and 20% steel and 80% PLA. So we have optimized the temperature that at what temperature that we can print these filaments. If we like print on the normal temperature, so we can't make it because you can see in that it's the printing will stop and it will be mostly it will be more porous as compared to the normal printing. So you can see that this is the Ultimaker. So it's printing the battery pack. So after the material preparations, so we start like the testings because the battery thermal management system. So we know we need to know that how it's work with the battery conditions. So we have environmental chambers. So we have fixed the temperature and 20 Celsius, and then we have a battery tester to test the battery at different charging and discharging rates. So this is all the setup for our testing, validation, and experimental setup for. So the battery casing, we have installed some sensor in the battery pack. The sensor is a highly sensitive to measure the temperature of the material and measure the temperature of the chamber and the material, especially the material from top, from bottom, and from the middle of the battery packs. So battery thermal testing and validation. So mostly EV industry in UK, especially in the UK, they are using a cylindrical batteries. So lithium ion battery, and we have tested our material on 18650 cylindrical battery, and the temperature is the chamber temperature is fixed at 25 Celsius. And the charging rate is a 1C, that battery will charge and discharge within 1C. And it's a continuous charging because we want to know that whether what will be impact like if is a continuous charging and discharging of the battery, how the material will like behave with the temperature of the batteries. So you can see we have a printed battery pack, and we have made this all the setup in Northumbria University. I will quickly go through the results. So this is the microstructures. So we have printed the material. So the good thing is that we have to do the microstructures of the different filament, that how it's look like, because it's very thin, and the thickness of the printing layer is 0.1 to 0.2 mm thickness. So we want to see the what's exactly the material look like. So you can see the different material have a different morphology, and like this is a PLA, PVA, PETG, ABS. But we have, when we have introduced like the stainless steel and the carbon fiber, the morphology of the printing material is changed. So you can say this is just only 1% copper with PLA, and this is the 20% stainless steel with 80% PLA. Then we have done some thermal conductivity and density of the material, because in battery thermal management system, this two things is very important. First is the thermal conductivity. If it's a thermal conductivity is good, and then the second is the density. So we are trying to find the material which have a less density and high thermal conductivity, because if it's most of like the metal material, they have a really good conductivity, but because of its weight, let's say we use the copper have a very high thermal conductivity, but we can't use as a battery thermal management systems in different filaments, because it will increase the weight of the battery pack. So we are trying to find the material which is less dense and have really good thermal conductivity. So that's why we have a tune material with different metals and the carbon fibers. So we have a ABS, PLA, and PHG. First, we have take like the bulk, the commercial materials, and then we have printed like over material which have we make make with over filament maker. Then we have test the thermal conductivity and density of that material. So testing condition for the density is we have tested with the immersion method, that we have put that material in in water, and then we measure the density and thermal conductivity of the material. So the temperature is like at the room temperature, like 25. We fix the temperature 25 Celsius. So you can see the samples. We have not put like whole battery pack. So we just take like 25, 30 by 6 mm samples. We have printed the samples, and then we have measured the density and the thermal conductivity of the materials. So you can see like we have the best material. We have like the PVA and the carbon fiber. So you can see the PVA and PVA density, and then the PVA thermal conductivity. So here then we have test over material at 1C charge and discharging rate of the battery. It's almost 140 hours. We continuously charge and discharge the battery for more than like 140 hours. So we have tested, and we have plot like the graph are from 0 to 140 hours with the different PLA, ABS, PETG, and then the PLA. So I will show you in the next graph, like because like very tight plotted. So I will show you, because I just want to show you that we have done from 0 to 140 hour to compare the result of different materials. So here you can easily see that we have different materials. First, I have plotted from first 5 hours, then I have plotted last like 136 to 140 hours. So from our conclusion, like PLA plus 20% carbon fibers. So you can see in first 1 to 5 hours, and then you can see like after it's almost maintained. So it's already maintained, because it's a continuously charging and discharging material, not decomposing. and it's showing really good, like the temperature is not increasing. But if you see in the case of PLA and 80% steel, the temperature is increasing. And if we go for the PVO also, it's bit increasing, but it's have really good efficiency as compared to other materials. Then we have measured the percentage of capacity, because in it's the story, all the story we have made for the capacity, that how we increase the capacity, how we make the safe battery. So from all of these material, we have a PVA which have a really good capacity, and it's maintained the capacity. You can see in here. So PV have a really good, then we have a carbon fiber, PLA and 80% steel have a good like percentage capacity, but we can't use because 80% steel and 20% PLA increase the weight of the battery pack, so we can't use. So just as a comparison, that I just want to show that we can steel have a really good like thermal conductivity and PLA with PLA, but the problem is that it will make very heavy. It will make the battery pack very heavy, so we can't use it that material. Then we have done some validation of experimental data through the modeling with using a COMSOL. So we have choose the same condition, and we use like 1865 cell, and the nominal capacity, everything is the same, the charging voltage and everything is the same as for the experiment and same for the simulation. So you can see this is the simulation data is almost like close to the our experimental data. So we have done all the data from 0 to 140 hours, and you can see the simulations, the CFD of the battery thermal. It's a single cell, so we have done the single cell simulations. And then recently we have done some battery pack simulation, so you can see the video of like the simulation for the whole battery pack. So you can easily see that during charging and discharging, temperature is increasing and decreasing. And the future work, so we are planning that for the pure PCM, so we are trying to add some paraffin waxes and salts and different inorganic bio-based PCMs. And we are trying to optimize, because if we put the pure PCM, so it will leak out from the battery pack, because the temperature sometime during a fast charging, it's go more than 120 Celsius. So maybe, so the PCM will leak out. So we are trying to optimize the PCM, that what kind of PCM and PCM we can mix in that material. And then we have carbon. So we are also trying expanded graphite. We are already like optimized carbon fiber, which have a really good results than the carbon nanotubes and graphenes. Metal, we also using some metals, and we also have a plan to test some more metals in this battery thermal management systems. For the future work, so we have a plan, another plan that we also have we have a plan that we will also try all our material in the medical application, because in all medical and all telecommunication and test and different type of industrial power tools, all the mechanicals and the electronics equipment use the battery. So we are trying to make specialized battery pack for all the materials. So you can see the application of all the battery thermal management system for different fields. We can use medical, telecom, like the test and manufacture, and different type of aviation and militaries, and health, and especially health and the personal safety equipments. So recently we have present our work in the Northern Accelerators, and we are working with the Northern Accelerator. We have make special type of battery recycling jar for the northern accelerator, and then we have make special kind of mix of different materials. You can see here one of the companies called Synthesis in UK. So we have developed a special material for them, because they need a special kind of material to control the temperature of their IoT device. So we have fabricated, because this is basically carbon fiber and PLA. And another medical company, so we have delivered these samples. This is some mouthpiece which used in the medical field. So we have a printed, this is the antibacterials and PLA and some other materials. So we are working like, we are not just want to publish the paper and something like that. We are trying to commercialize our product. So we have also filed a patent. So the patent file is still with the university, and hopefully it will be published soon. And special thank to Rana Shakur from Qatar University. And then we have our Dr. Mamlouk from Newcastle University, and Abdul Wase, Hertford University, and Dr. Edward Bentley from Northumbria University. These guys really help like developing the materials, and they also help Dr. Shahid and me to develop the lab in Northumbria University. Thank you so much for your attention. If you have any question, please, I'm more than happy to answer.
Thank you very much, Dr. Rana Faisal, for sharing your findings and contributions, which are very significant in the field of thermal management of batteries and other devices. So far, we haven't
one more thing. Like it's open invitation for all my Pakistani community. We are more than happy for the collaboration. If you need any help regarding the extrusion of the different type of filament, if you want to make different type of filament and you want to print different type of, I'm more than happy to help you.
Thank you very much, Dr. Rana Faisal. It was very generous of you. And we are very sure that we will get back to you on this topic and to discuss the details. And again, we are very grateful for your time. And,
thank you so much. Thank you.
And the knowledge that you have shared with us today. Thank you very much.
Thank you. Thank you. Thank you so much.
Dear audience, now I would like to introduce our next speaker, Ms. Amreen Chaudhary, who is affiliated with Chemical Engineering at University Technology, Malaysia. Her presentation focuses on the intriguing topic of nanocellulose as reinforcement in paper processing and paper products, the challenges and future perspectives. Her presentation, I welcome Ms. Amreen Chaudhary to share her expertise and insights on this innovative subject. Ms. Amreen, the forum is yours.
Thank you so much. Assalamu alaikum and good afternoon, everyone. Is my voice clear? Hello, is my voice clear?
Yes, you can present.
Okay, okay, all right, sure. Thank you. All right. Okay, assalamu alaikum and good afternoon, everyone. I'm Amreen Chaudhary from School of Chemical and Energy Engineering, and I graduated recently from University Technology Malaysia, UTM. So today my presentation topic will be nanocellulose as reinforcement in paper processing and paper products. And I will also be talking a little bit about the challenges and future perspective about the nanocellulose being used in the papers and the paper industries. So moving on, this is my table of content. So I will be doing a brief introduction about nanocellulose, and I will be talking about the working mechanisms of nanocellulose in the paper matrix, Nanocellulose as paper-making additives and reinforcement, nanocellulose reinforced paper sheet properties, and also applications of nanocellulose in specialty papers. And finally, I will do a short conclusion for my overall presentation. Okay, so what is a nanocellulose basically? So nanocellulose is something that is derived from cellulose, and cellulose is something that we get from like plants, trees, like that we can get like naturally. So basically the main part of the plant where we get the cellulose from is the plant cell walls. So we get this material from the plant cell walls and we then modify it, structure it to form nanocellulose. And why is it called nanocellulose? It's called nanocellulose because the structure is nano. It's nanoscale fibers and it has nanoscale particles as well. So the main reason why we chose nanocellulose for making paper is because it's sustainable. Sustainable means like you can renew it and it's also biodegradable. It's very strong, and on the other hand, it's also very lightweight. So it has a low density, and being strong, it has a high tensile strength as well. And most of the times, the nanocellulose are transparent and it has very good barrier property. So transparency is good for optical properties. So transparency for optically clear applications. This is where we need this property. And it also has excellent gas and liquid barrier properties. So in the picture over here, to my right side, it shows a detailed picture of how a nanocellulose looks like how we can get it and what it looks like when it's suspended in water, and just a little bit about the detailed structure of the nanocellulose over here. So it's showing us a cellulose fiber, it's showing us macrofiber, microfiber, and also the elementary fibrils as well. So yeah, it's just basically like a detailed structure of the nanocellulose over here. And then moving on to the next part is basically applications of nanocellulose, or where do we use nanocellulose? So nanocellulose has a variety of applications, among which is very famous, which is textile. So nanocellulose can be used in textile industries, and then in some of the industries, they use it to capture carbon dioxide to reduce like pollution in the air. We use nanocellulose to produce food packaging materials like our packets, our coffee cups, stuff like that. And then we can also use nanocellulose in wastewater treatment. We use it in our food containers, our the food packaging, like maybe we can use it for our chips wrapper or chocolate wrappers. Nanocellulose also, they are used in biomedicine, wood adhesives, cosmetics, and also their use, you can also see their uses in electrical and optical optical industries as well. So, all right, so since my topic is mainly focusing on the use of nanocellulose in the paper industry, so I would like to focus on that one now. So now I'm going to be talking about the role of nanocellulose in the paper industry. So nanocellulose has gained importance in the paper industry due to its like unique properties, such as it having like a very high strength, it being flexible, and also sustainable. So these three properties are very like all of the industries want these three properties in a product they're making. So these three properties makes nanocellulose one of the best choices for the paper industries as well. Nanocellulose can also be used as a reinforcing agent in paper production, which is my topic, and this helps to improve the paper's strength and durability. It can also be used to enhance paper's optical properties, making it more suitable for our printing and our food packaging, chip, and any other packaging applications, such as like the packaging that we use for our clothes, or maybe like the cardboard boxes and stuff like that. And its use in the paper industry mainly can lead to the development of lightweight, high-performance paper products. So nowadays, like the industries and researchers are trying to find out new ways of using nanocellulose into like paper and make them into paper products, so that we can get like very highly durable and lightweighted paper products. So Next is I'll be talking about the working mechanism of nanocellulose in the paper matrix, because this is the main important part of using nanocellulose in paper products, because the working mechanism of nanocellulose has to be compatible with the paper matrix as well. So how does nanocellulose usually work in a paper matrix? Is first, number one, we do source and isolation, meaning like we select sources from which we want to get the nanocellulose from. So it can be like different type of plants, it can be from sugarcane, it can be from maybe what else, like any other plant around us. We can select a source, particular source for the nanocellulose, and then we isolate the nanocellulose from that particular source by using like some kind of physical and chemical processes. And when we isolate them, we get two types of nanocellulose. One is CNF, another one is CNC. So we can use CNF and CNC, both of them, we can use both of them to make our desired products in the industries. So first we choose a source and we isolate the nanocellulose using some chemical and physical processes, which one is suitable for our process. And then next what we do is we do reinforcement. So what is reinforcement is basically just the nanocellulose that we extracted just now. We just reinforce it. We reinforce the cellulose fibers in the paper matrix, and we just add it with the paper so that we can reinforce it in the paper matrix. And by doing this, we actually enhance the overall strength and the mechanical properties of the paper. And then next is doing this, since I already mentioned about enhancing mechanical properties, so it also improves the barrier properties. So how does it do is, nanocellulose creates a barrier in the paper matrix as soon as it enters the paper matrix. So it restricts the entering of any kind of gases or liquids or any other substances which can be harmful to the product that we are making. Let's say we are making a food packaging material. So we want to protect our food from bacterial growth or maybe from the moisture in the air. We want to keep it like fresh and we don't want it to go stale. So at that time, we keep in mind that we have to use the food packaging material made from nanocellulose, because nanocellulose can help the food packaging material to restrict the entering of any kind of moisture or liquid or any other harmful substances that can make your food go bad. So that's one. And then also using nanocellulose enhance the printability, meaning that using nanocellulose, it actually improves the optical properties of the product that we are making. So by doing that, it enhances the printability. So whenever we print something, how can we see the letters clearly on the paper? It's because when we make our paper or other products or packaging from nanocellulose, it increases the optical property of that particular product, and it can also, by doing that, it enhances the printability as well. And then the working mechanism of nanocellulose is in such a way that it also reduces the weight of the paper, and then it also makes it very sustainable. And also in the future, if the researcher wanna modify the nanocellulose into something else, they can also do that, and they can use like different methods for functionalization. And so that's why nanocellulose structure is made in such a way, nanocellulose structure, it allows us to functionalize the nanocellulose and also modify it into more sustainable, into more enhanced paper products. And over here on the right side, the second picture actually shows the bonding of nanocellulose with the paper matrix. So the fiber, the nanocellulose fiber, it actually bonds to the paper matrix by hydrogen bond. So when we put it into the paper, it creates a hydrogen bond. The structure is in such a way that it can create hydrogen bonding with the paper, and that's how it can actually make the paper very durable, give it strength, and also improve the barrier properties of the paper. So moving on to the next one, nanocellulose can be used as reinforcement, and also we can use it as paper making additives. So nanocellulose can be added to pulp. Nanocellulose can be used as a reinforcement of base papers, like the usual normal papers that we use. We can use it as a reinforcement over there. Nanocellulose composite the composites of nanocellulose can be used as a reinforcement of base paper, and nanocellulose base coating agent for paper and paper products. So we can also come up with nanocellulose base coating agents, and those coating agent can be used for papers and paper products as well. Next is